Thank you, ladies. I appreciate it. Awesome. All right. Good morning, everybody. This is January 25th. A couple of announcements to start off the lecture. First of all, WebAssign homework is due on your first WebAssign homework is due on January 28th. So that's just in a couple of days. Two assignments: the assignment for section 7.1 and the assignment that covers section 7.2 and 7.3. Those are both due on the 28th, and those are always due at midnight on the due date. So that it's at the end of the day on the 28th. I did get a grace period extension. I did send that message out to everybody just in case you didn't get it, but I did send that by remind yesterday. And so the grace period for everybody in WebAssign is extended to January 31st, I believe. And so at the end of the day, the 31st. So what that means is that you ought to be able to continue to work in WebAssign. Even if you have not purchased an access code, you can continue to work in WebAssign as an ordinary situation until the end of the day on the 31st. And then if you have not paid for an access code after the 31st, then you just will still be able to log into WebAssign, but you won't be able to log into the course, and you won't be able to do any of your homework. So just make sure that you get it. You try to get that access code purchased before the 31st if you can. Now, if you go after the 31st, then you'll still be able to go ahead and purchase the access code, and none of the work that you've done ahead of time or before that will have been lost. It'll all get saved. So then you just pick up wherever you are at that point when you've purchased your access code. Okay, so try to get that done as best you can. If you have any questions about that, let me know. Access codes are supposed to be in the bookstore by Monday. I've been in touch with the people at school, in the department, and in the bookstore, and I think we've gotten some things straightened out. And so there should be access codes for this course in the bookstore by Monday also. So hopefully that covers everybody, and you should be able to get yourself taken care of as far as WebAssign goes. Online office hours, I'll continue to remind you of this every class meeting. Sunday and Tuesday, 8:30 to 9:30 in the evening, and then Tuesday, Wednesday, Thursday, 11 to noon. And so don't hesitate to come by for help if you have questions about material. I'll be happy to help you out. And that's the way to get probably a more efficient answer. Some of you have been messaging me through WebAssign, which is fine, by the way, but it may take a little time sometimes to get a response. And, the response is just going to be a written response. Whereas if you show up to online office hours, you can actually talk to me in person. So, online office hours are always, to me, the first line of defense. And so try to take advantage of those if you can. Exam 1 is rapidly approaching. The window for that is February the 8th through the 13th. And I didn't write this on here, but remember that before each exam, I will be on campus for on-campus office hours. And so I will be on campus on February the 7th and 8th for some office hours. I think I'll be on campus for 4 office hours altogether. I'll talk more about that next week, but I will be on campus on February the 7th and 8th. So if you want to actually come by and talk to me in person, you'll be able to do that. The exam is not a WebAssign test. It's not on the computer. It's a paper and pencil exam. It's a traditional math test. You write all your work on a sheet of paper, on the test itself, actually, and you turn that in. The testing center will scan that test and send an electronic copy to me. I'll grade it electronically on my iPad. And then if you want a graded copy back, then you will email me, and I will email you back a graded copy of your test. And that seemed to work out pretty well last semester. You can use a scientific calculator on exams, just so you know that also. It's really not going to be necessary, to be honest with you, for the most part, but if you feel like you need that to fall back on, you will be able to use a scientific calculator. I will have a review for the exam posted by, the 30th, 31st, somewhere in there. So that's in the middle of next week. So the review will get posted pretty quickly here. And then finally today, we're going to go through in a review of factoring, review all the things we've talked about with factoring polynomials, and then we're going to look at our main topic for the day is looking at using factoring to solve quadratic equations. And so let's get started. If there's no questions from anybody who's with me today live, then we will get started. So I guess there's no questions. So, so let's talk about a little factoring review first of all. Now on your review for the exam next week, there's going to be this big section. I'm going to have a lot of factoring problems on there. So you're going to have a lot of practice problems that you'll be able to use to help you prepare for the test. And the deal with the test is, all the techniques for factoring that we've discussed, we're going to all be mixed together. So you have to be able to be pretty good at going into a problem and walking yourself through the process for which method would be appropriate for the problem that you're talking about. So let's deal with this. Let's first kind of write down our little flow chart. We've already done this before in lecture, but I want to write this down again. So the first step always, remember, is to take out a GCF if there is one. We'll always look for a GCF when you're factoring a polynomial. See if there's something common. That is an easy step to overlook, and frequently that gets students into trouble. So it is one of the single most common mistakes students make, probably, when you're talking about factoring a polynomial. On the exam, what I would do if I were you is I'd actually write down the letters GCF at the top of this section on factoring, just to remind myself, hey, I need to go through these problems. On every one of them, I need to look to see if there's a GCF first. And then after that, remember what we did is we looked at the number of terms that a polynomial had. And if a polynomial had 4 terms or more, though we really haven't looked at any that are worth more, then we're going to try grouping. Now, what we have looked at in class is we've looked at grouping problems that group 2 terms and 2 terms, right? If you have a polynomial with 4 terms, you group the first 2 together, group the second 2 together, the second group of 2 together. Polynomials with 4 terms sometimes will factor by grouping where you group 3 terms and 1 term. We're just probably not going to see any problems like that, but that is a possibility, definitely. Also remember that with grouping, it's possible you may have to rearrange the terms. And we looked at a problem or two like that in lecture where you actually, it didn't factor by grouping like it was written, so you moved the terms around, and then it did factor by grouping after you moved the terms around. All right. And then we looked at polynomials with 3 terms. In other words, trinomials. And so the way I divided this up is I looked at easy trinomials. Easy trinomials were things like this: x squared plus 8x plus 15, right? Lead coefficient is 1. And remember, with these trinomials, it's always the case that you're just looking for factors of the constant that add to give the middle term. Right, so easy trinomials always have this nice, very straightforward way of factoring. And then we had the not so easy trinomials. And, these can be somewhat challenging sometimes. And there's many different methods for factoring a not so easy trinomial. Lots of different ways that you could do that. And so we've just looked in class, I purposely only looked at one method for factoring a not so easy trinomial because I didn't want to get bogged down in a lot of different possibilities. A lot of times that can cause more harm than good, really, ultimately. And so, if you've seen other methods besides the trial and error method that I used, remember I used trial and error. But if you have a grouping method or a box method or the AC method, there's all sorts of different methods for factoring trinomials. I don't care which one of those methods you use. You just need to have a method that's going to work for the polynomial that you're dealing with. And so I don't really care. So an example of a not so easy trinomial might be something like this: 8x squared minus 9x minus 3, right? The lead coefficient is not 1 here. All right, and then we looked at, and we'll talk about factoring all these in a little bit. And then we looked at perfect square trinomials. So perfect square trinomials were ones that actually factored as the square of a binomial. So as an example, something simple like this one, x squared plus 14x plus 49, which factors as x plus 7 squared. Right, that's an example of a perfect square trinomial. And remember what we talked about, the method we looked at in class was that if the first and last terms were perfect squares and you multiplied those together and then doubled it, multiplied by 2, right, did you get that middle term? And if you got the middle term, then it was a perfect square trinomial. All right, and then finally we finished with 2 terms, looking at polynomials with 2 terms. And remember, we're talking about binomials here. And we've got 3 very distinct patterns to look for there. The difference of squares, which factors a plus b times a minus b. The difference of cubes, which factors a minus b times a squared plus ab plus b squared. And then the sum of cubes, which factors a plus b times a squared minus ab plus b squared. And I would definitely write those 3 patterns down on my exam when I take it, right? You won't have any notes with you, but if you actually write those down, then you don't have to remember them as you go through the exam. So, all right. So this kind of lays out the process that I've talked about in class for factoring a polynomial. And so let's look at some of these some examples here. So these are problems that I'm picking out of section 7.5 of your textbook. And this is on page 859 of that textbook. And so I'm just going to go through and just work through some problems here, and let's see how we do, right? Let's kind of pick the correct method and everything. So this is problem 282, where you have b squared minus 17b plus 60. All right, so this is what I'm thinking about as I'm going through this problem. I'm thinking, first of all, no GCF, right? Always think GCF at the beginning, but there's nothing that's common to all these terms. Next thing I look at is this is an easy trinomial because the lead term is got a coefficient of a 1. And so that means I'm looking for factors of 60 that add to give negative 17, right? And so, what you ought to do, first of all, since they add to give, or they multiply to give 60, but add to give negative 17, I do know that they both have to be negative, right? That's the only way that's possible. And so I write down the factors of 60, 1 and 60, 2 and 30, 3 and 20, right? None of those are going to work, but then then you have 4 and 15, lots of factors of 60, and then 5 and 12, and there you go. 5 and 12 are the 2 that are going to work, because those are going to I'm going to be able to use those and add them to get negative 17. So this factor is b minus 5 times b minus 12. And remember, if you write b minus 12 times b minus 5, absolutely not a problem. It doesn't matter what order you write this in, so both are okay. Since it's multiplication, it never matters what order you write the terms in. All right, so that was problem 282. Please stop me if you have a question as we're going through this. You know, this is what I'm thinking about over here on the side, and then I'm actually working out the problem. So, all right, this is problem 288. You have 49b squared minus 36a squared. So as far as thinking about this problem, first thing is there's no GCF, right? There's no term, there's no factor that's common in both of those terms. 49 and 36 don't have any common factors. Next thing is it's a binomial, right? So when I see that it's got two terms, then I'm thinking, is it one of these three patterns, a squared minus b squared, a cubed minus b cubed, or a cubed plus b cubed, right? If it's going to be written as a multiplication problem, it's got to fit one of those three patterns. And because of the constants and the variables, the only one that's possible is the squares. And so the first term is 7b squared, and the second term is 6a squared. And so sure enough, it is a square minus a square. And so I can write this as a multiplication problem. It's just 7b plus 6a times 7b minus 6a, right? A plus b times a minus b. Right? As soon as you see it's a binomial, you're restricted to one of those three possibilities as far as it being squares or cubes or difference of cubes or sum of cubes. All right, so we're kind of looking at a lot of different techniques. But this is the way the test is going to be arranged. There's going to be a lot of different methods to use for factoring. They're all going to be mixed up. This is problem 302. We have 12ab minus 6a plus 10b minus 5. All right, so the first thing is there is no GCF in this problem, right? And remember, I don't care how many terms there are. I'm first looking for a GCF. And there aren't any GCFs in this. There's no common factor to all four terms. Next thing, we count the number of terms, and we notice that there's 4 terms in this polynomial. So that means try grouping. Right? As soon as you see 4 terms like that, you're going to try to group. And remember, what we want to do is we want to first try to group the first 2 and the last 2 and see if that works. If that does not work, then we try to rearrange it and see if we can force it to work with a different arrangement. All right, so the first group, the common factor there is 6a. And when I take out a 6a, I'm left with 2b minus 1. The second group, I take out a 5. There's a common factor of 5. And when I do that, I'm left with a 2b minus 1. And yay, that's what we're looking for, right? Because I'm left with something that's common. This has got to be the exact expression, exactly the same expression there. And so now it is, and so now there is a GCF. All right, so we've created a situation where there is a GCF. So we factor out that GCF, which is 2b minus 1. And then we're left with 6a plus 5. Right, and we've got it. So that's our final factorization there. All right, so I'm not getting anybody to stop me here. So I think everybody is okay with those of you who are with me today live. Let's look at problem 308. You have 25x squared plus 35xy plus 49y squared. Okay, so now this is an interesting problem. First of all, there's no GCF, right? Nothing that's common to all three of those terms. It is a trinomial, and it is a trinomial, and it is, first of all, it's a not so easy trinomial because the lead coefficient's not a 1. But is it a perfect square trinomial? That's a possibility here, and we need to check it to see if it's a perfect square trinomial. And the reason why I would think that is because the first term is a perfect square, right? It's 5x squared. And the last term is a perfect square also, it's 7y. So remember, when that's true, that the first and last terms are perfect squares, it's possible it's a perfect square trinomial. Now remember, what you do is you take these two numbers and you multiply them together. So when I multiply those together, I get 35xy. But then remember, I'm supposed to take that and then I double it to see if it's the middle term. So I multiply by 2 and see if I get the middle term. And notice I don't, because I already have the middle term, 35. So when I double it, I get 70. So this is not a perfect square trinomial. Okay, so that maybe was unexpected, but not a perfect square. It does not fit the pattern. And so what are we going to do here? Well, we're going to treat this as a not so easy trinomial. Then treat as a not so easy trinomial. And I will use trial and error. You might use a different method possibly. And that is perfectly okay with me. I have no problem with that at all. So let's write down the trinomial again. You have 25x squared plus 35xy plus 49y squared. And so remember, the way I've talked about doing this is I've talked about writing down the factors for 25 and 49. So the factors of 25 are 1 and 25 and 5 and 5. And then write down the factors of 49. 1 and 49 and 7 and 7. And remember, with trial and error, what we're doing is we're looking for two pairs of numbers here, or two numbers rather, that add to give 49. And that's add because of this plus sign right here. So that means we're looking for two numbers that add. And what we've got to do is we've got to pick a pair out of the first group and pick a pair out of the second group and see if we can create a situation where we get a 35 as the middle term. All right, so let's try this. If you picked, I'm going to write down a lot of the different combinations here. So if we picked 1 and 25 and 1 and 49, right? 1 times 1 is 1, and 25 times 49, well, that's just a really big number, so that ain't going to work. And then remember, what you can do is you can switch it, and you can multiply 1 times 49, which is 49, and 25 times 1, which is 25. You're looking for two numbers that add to give 35, and that ain't going to work either, right? That's a 25 and a 49, so no. So this combination doesn't work. All right, so then we go on, and let me try 1 and 25 and 7 and 7. I'm going to be very methodical about this. I'm going to try all the different possibilities. We're looking for a 35. So I take, I'm going to take 1 and 7, which gives me 7, and 25 and 7, which gives me 175. That doesn't work. So then I switch the multiplication. And so I take 1 times 7, which is 7, and 25 times 7. Notice it's really the same combination. That's 175. That ain't going to work. So those two do not work together. So no, right there. So we've eliminated 1 and 25 as being a possibility. All right, so the next thing we do is we go on and we check 5 and 5. So 5 and 5 is out of the first group, and 1 and 49 is out of the second group. 5 times 1 is 5. 5 times 49 is 235. I'm sorry, 245, certainly doesn't work. And notice because the first two are 5s, if you switch them, you're getting the same multiplication. It's just opposite order, but you're getting the same numbers. So that combination does not work. And so we are finally down to 5 and 5 and 7 and 7. This is our last shot at this. And so I've got 5 and 7 and 5 and 7. Both of those give me 35. That doesn't work, right? Because those don't add to give 35. And so, and if you switch them around, obviously you get the exact same multiplication. And so what have we just done? We have eliminated every possibility. We have eliminated every combination here. And so what's my conclusion? Those of you who are with me live then, what's my conclusion on this problem? I've gone through and I've eliminated every possibility. What?
That is prime.
It's prime, that's right. Yep. And that's what you would write. Now, be careful on a test. I'm probably going to give you a prime polynomial somewhere on the exam. You have to write the word prime. If you just have a bunch of work there and then no answer at all, then I really don't know whether you knew that it was prime or not. And so, yeah, and the way I'm looking at it is I'm saying, well, they started the problem, but they really couldn't finish it, and they really didn't know how it worked out. So you need to write the word prime down, or certainly you could write not factorable. If you actually wrote those words down, I'd have no problem with that, because those mean exactly the same thing. Okay? And so there's no way to write this trinomial as a multiplication problem. All right. So any questions? Any questions at all?
No questions. No questions.
Okay. Good. Next problem I want to look at. This is problem number 305 in that section. Number 305, and it's u to the 5th plus u squared. Looks like a pretty simple expression. And so we're interested to see how this works out. Remember, what's the first step is there a GCF? And in this case, the answer here is yes, there is. Because there is something common between those two terms, and that is u, right? There's a u in both terms. And remember, the rule is you factor out the smallest power that's in both terms, right? Factor out smallest power UC, right? And so for the u's, there's a u squared up there. That's our smallest power. And so you take that out. That smallest power is the largest one that's common to both terms. So we factor that out, and then we are left with u cubed in the first term. And in the second term, we had two u's. We took both of them out. So remember, that means you're left with a 1. So you have u cubed plus 1 left in the parentheses there. That's our binomial. And so then what you have left is a binomial. And so remember, since it's got two terms in it, now you're saying, well, is it one of these three patterns? Right? And now, because it's an addition problem, the only one that would even be possible is a cubed plus b cubed. That's the only one that's addition. Don't forget that a squared plus b squared is prime. That's why I don't write that one down, because that one's not factorable. U cubed plus 1 is the sum of two cubes, because the first term is a perfect cube, u cubed. The second term is also a perfect cube, because it's 1 cubed, right? 1 cubed is equal to 1. And so this is the sum of two cubes. And remember, let's write down the pattern for that. So the pattern, remember, is that a cubed plus b cubed is a plus b times a squared minus ab plus b squared. All right, and A and B in this case are both, A is U, so this is, well, let me go ahead and go back to the original color here. So I've got U squared, my GCF I continue to write down, and then I have A plus B, that'd be U plus 1. And then this trinomial is always A squared minus AB plus B squared. And so that's going to be a U in those first two parentheses, and a 1 and a 1 in the second set of parentheses, second two sets of parentheses there. And so you end up with U squared times U plus 1 times U squared minus U plus 1. And there's our factorization. So it ended up being, even though it's a simple polynomial at the beginning, it ended up being that there's a decent amount of work to do in that problem. All right, so I think we're doing okay. Next problem I want to look at is number 286. We have 75m cubed plus 12m. All right, so on that problem, GCF, yes, there is a GCF there. All right, because between 75 and 12, first of all, there's a common divisor there of 3. And between m cubed and m, there is a common m there, and so I take out m to the first. And so that leaves me with 25m squared plus 4. And now I don't know how many times, I bet probably over the years, if I gave a problem like this on the test, I get at least half of the people not finish this, or not leave it like that, but factor it one more time. And they would write this as 3m times 5m plus 2 times 5m minus 2. Or 5m plus 2 times 5m plus 2, possibly. Both of those are wrong. Remember that, see, these are both wrong. Remember that this is the sum of squares right here. 25m squared plus 4 is the sum of two squares. That's a squared plus b squared. And a squared plus b squared is prime. Right? So there is no way to take 25m squared plus 4 and break it up as a multiplication problem. So what do you write in this problem? Do you write prime down? No, because it did factor at the beginning. Because the 3m was common. So this is your answer right here. Right? That's the factorization. It doesn't factor beyond that at all. Right? And so it's really easy to make that mistake and to go ahead and factor that, try to factor that polynomial again. Now notice that if this had been 75m cubed minus 12m, now you're going to end up with the difference of squares, right? When you take out the 3m, you're left with 25m squared minus 4, and now it's the difference of two squares, and it factors 5m plus 2 times 5m minus 2. Okay, so you have to really kind of pay attention there and be careful when you've got the sum of squares like that. All right. Next problem I want to look at. All right, so let's say I have, and I'm, hold on here, I'm making this problem up as we go along. Okay, just making sure that I had this correct before I wrote it down. So this problem is 3a. I'm sorry, I said I had it right. Now I'm going to write it right. So this is 6a x squared minus 24a minus 14 bx squared plus 56 b. Right, that's a 56b at the end there. Let me rewrite that. So it looks more like a 5 and a 6 and a b. All right. So what's your first step here? First step is there a GCF? And the answer here is yes. There is something that's common to all those terms. Let me ask you guys that are with me today live, what's common to all 4 of those terms?
Is it 3?
Well, let's see. 3 divides into 6. 3 divides into 24. 3 does not divide into 14. Right? So it's not 3.
Oh, do we have to group first?
No. Remember, what's first?
Yeah.
What's first is to look for a GCF, Raina. And so if you're looking for a GCF, it's got to be in all 4 of the terms. Right? So you're not worried about grouping yet. And I know you've got 4 terms there, so you're thinking grouping in your head, but don't get to grouping yet until you've looked to see if there's something common to every term. Taylor, do you have an idea?
2.
What?
2?
Yeah, it's 2. There is a 2 that divides into all 4 of those terms. And so take that 2 out. Right? The GCF is 2. So Raina, remember, you were looking at grouping, or you were thinking about grouping, and that's a common mistake in a problem like this, because you see 4 terms, you're thinking grouping right away. Don't think grouping right away. Instead, always think GCF for all the terms first, and then worry about grouping after that. So I'm going to take the 2 out, and that would leave me with 3ax squared minus 12a minus 7bx squared plus 28b. Right? And now I've got that taken care of. Now I've gotten the GCF taken care of. Now worry about grouping. Right? So now, Raina, you go on to dealing with grouping. And so I'm going to try the first 2 terms and group those, and try these last 2 terms and group those. So let's see what happens. So in the first group, I'll also use big parentheses here and then little parentheses on the inside. The first group is a common factor of 3a. And when you take out the 3a, you're left with x squared minus 4. And then in the second group, there's a common factor of, first of all, don't forget that it's a negative because the first term is negative. And there's a 7 and a b that's common in those 2 terms. And when I take the 7 and the b out, a negative 7 and a b, I'm left with x squared minus 4. And then I put the big set of parentheses down there. And I have successfully gone through and dealt with the GCFs in both of the little groups. And sure enough, I was left with a common factor, x squared minus 4 in there. So don't forget this 2 that I've taken out. Remember, it just continues to trail along as a factor now. Don't make it disappear. So the common factor is x squared minus 4, so I take out that x squared minus 4. And I'm left with 3a minus 7b. And so I did factor it by grouping. Now, would you have to worry again because I've got 2 binomials, and sometimes it's possible that one of those binomials might factor again. And now look at the binomials. You frequently, most of the time, the binomials are not factorable, but in this case, notice that this one binomial is a square minus a square. And so that x squared minus 4 is the difference of 2 squares. And so that factors x plus 2 times x minus 2. Right? And then the 3a minus 7b just comes down for the ride, like that. So, what did I do here? I took the x squared minus 4, and I factored it as x plus 2 times x minus 2. right? And now I can't factor anything else. So notice this problem was ended up being, a substantial problem because it had a GCF, and then you had to group, and then finally you looked at the binomials and found the difference of two squares there. So there was a lot to do in this problem, right? And so definitely what I would say is I've gone through these problems so far is that you need practice. The more experience you've got with these problems, the better off you're going to be. Now, I know you're saying to yourself, well, gee, he can look at these problems and he just factors them like with his eyes closed. But you have to remember that I've been doing this a long time. I've been teaching algebra classes for 36 years. And so I'm like several thousand problems ahead of you, right? And so why can I look at most of these and just kind of go through them really easily and factor them? It's because I've factored so many different polynomials over the years. I've just got a lot of experience doing that. That's what you need to do between now and the first exam is you need to practice a lot of factoring problems because this is going to be a significant number of points on your first exam, right? And so, you're talking that the section on factoring is going to be worth probably 40 points of this test. And so, or 30 to 40 points at least. And so, you need to, that's something you can't overlook going into this test. All right. So now we're going to move on to talking about solving quadratic equations. And that's what we're going to look at for the rest of the day today. And we're still going to be factoring here, by the way, as we go through this. So we're talking about solving quadratic equations. And so the first thing we need to do is talk about what the heck a quadratic equation is and make sure that you can distinguish quadratic equations from equations that are not quadratic. And by the way, in my college algebra class, that was the very first thing we did on Monday is we looked at all the different methods for solving, or not on Monday, but on the first day of class, is we talked about solving quadratic equations and all the methods for solving it. There's 4 methods. Now, we're only looking at one method today. We reviewed all 4 methods in the first day in that college algebra class. Definitely something that in college algebra, your instructor is going to assume that for the most part, you can deal with quadratic equations without too much difficulty. All right, so first of all, what is a quadratic equation? It's an equation that can be written in this general form, ax squared plus bx plus c equals 0, where the a is not equal to 0. In other words, this term must be present. The other two terms, b and c, can be 0, so those other 2 terms can be gone, but that first term must be present. And so generally what we're saying here is that this is a second-degree equation, second-degree polynomial equation. That's what a quadratic equation is. So if you look at these 2 problems, let's say we have 2 plus 3 times 2x minus 1 equals 8 plus x. And then you have 2 plus 3x times 2x minus 1 equals 8 plus x. Those look like almost exactly the same equation, but they're definitely different. If you multiply everything out, just using the distributive property to get rid of the grouping symbols. Remember, by the way, on that first equation on the left, don't add the 2 and the 3 together first because that would violate order of operations. You have to take the 3 and multiply it by the 2x minus 1 using the distributive property. So after you've gotten rid of all the grouping symbols, notice that all the x's here are first degree, and so this is a first degree equation. This is a first degree equation, and we call first degree equations linear equations. Right? That equation is linear. On the other hand, the other equation, the second one that I wrote down, when you use the distributive property there, you get 2 plus 6x squared minus 3x equals 8 plus x. And notice this one has a second degree term. This is a second degree equation. Now, it's not in standard form, but it is a second degree equation. And so this is what we call a quadratic equation. Right? And so that's what we're talking about solving here, are those kinds of equations. Now, so we're going to look at one method for solving a quadratic equation in this section right here. This will not always work. And I'll talk about why it's not going to always work, and that we need other methods for solving quadratics that we aren't ready to deal with yet, but that we'll eventually deal with later in the semester. So the other thing we need, so now we know how to identify a quadratic equation, right? A quadratic equation is a second degree equation. And then the next thing we need to be able to do is we need to understand something called the zero factor theorem. And the zero factor theorem actually goes by several different names. So you may not see it written as the zero factor theorem, possibly. You may see it written some other way. But the zero factor theorem simply says that if you take two numbers and multiply them together, and the answer is 0, right? If a times b is equal to 0, so if that's true, then the only way that that's possible, the only way you could take two numbers and multiply them and get 0 as an answer, is one of them has to be 0, right? Which makes sense. You're taking two numbers, multiplying them together to get 0. One of them's got to be 0. There's no way you can take two non-zero numbers and multiply them and get 0 as the answer. Not possible to do. So we can actually use that zero factor theorem to our advantage to solve a quadratic equation. Because look, let's say we have this equation right here. Let's say we have x plus 3 times x minus 2 equals 0. And by the way, before I actually solve that equation, let me also point out here that the zero factor theorem works because of 0 and special properties of 0. This must be a 0 right here. It does not work for any other number, right? So it's certainly not true that if you have two numbers multiplied together and you get 3 as the answer, that one of the numbers has to be 3. That's actually garbage right there. There's no way that that's true. So it only works for 0. Right? It's a very special property for that number. And so that's something that's actually important as we look at solving quadratics, because sometimes you don't have a 0 on one side of the equation, and so you have to make sure that you have 0 on one side. All right. So in this problem, x plus 3 times x minus 2 equals 0. First of all, this is quadratic because even though I don't have an x squared written down anywhere, notice that if you took those two factors and multiply them out using the FOIL method, what happens? You do get a second degree term there, an x squared. So this is quadratic. And not only is it quadratic, but it's also written in a form where it's two numbers multiplied together to give 0. And so using our zero factor theorem, the only way that this could be true is if x plus 3 was equal to 0 or x minus 2 was equal to 0. That would have to be true. And so that's the great thing here, is that if you've got two factors multiplied together to give 0, the only way it can be a true statement is if one of them is 0, so you can automatically set the factors all equal to 0. And now notice that you end up with two really simple linear equations, and so you can solve both of those very easily by subtracting 3 on the first one on both sides, and on the second one by adding 2. And you've got the solutions to the equation. Negative 3 and 2 are the solutions to this equation. It has two solutions. What you'll find is that all quadratic equations have two solutions. Now, it's possible that the solutions may be the same number, so it looks like it's only one solution, but they all have two solutions. That's always true. Gee, that's pretty simple. You know, if you've got two numbers, two factors multiplied together to give 0, you can just set each factor equal to 0 and solve. So, you know, that's nice to be able to do that. So even though this equation looks a little different, first of all, it is quadratic, right? Because if I multiplied using the distributive property there, I do get a x squared in there, don't I? Because 7x times 3x is 21x squared minus 35x equals 0. So this is definitely quadratic. It has a squared term in it. It also has two factors multiplied together to give 0. Now the factors, one of them especially looks a little different than the original problem, but it's no different, right? Those are my two factors, 7x and 3x minus 5. So set both of those equal to 0. That's okay to do. And when you do that, when you set both of those factors equal to 0, now don't freak out on the first one, 7x equals 0. You're going to solve that for x by dividing both sides by 7. That's okay. I get all sorts of crazy things going on with a problem like that. And 0 divided by 7 is 0. That's okay. 0 is a solution to this equation. It's not a problem. On the second equation, I have to add 5 and divide by 3. And I get 5/3 as a solution. And there's my solution set, 0 and 5/3. No big deal, right? And so that worked out pretty easy. So this is looking good. All right, the next problem. Let's say I have -6 times 2x minus 7 times 3x plus 8 equals 0. All right, so in this problem, I've actually got three factors multiplied together to give 0, because I have -6, 2x minus 7, and 3x plus 8. Those are my three factors. Now, I do want you to notice that the -6, however, in this case, is a constant. It cannot be equal to 0. You do not get any solutions from that -6 because it's a constant. So what you can write in a case like this is just ignore a constant factor, because there's no way that that can be equal to 0. So there's no way you're going to get a solution from that factor. If you really wanted to, this is okay to do, you could actually just divide both sides by -6 like that. And what happens? The -6 just goes away altogether. And so if you want to, you can actually get rid of a constant factor that way and make it disappear altogether. Now be careful on the problem in the middle of the screen here. This was not a constant factor. That 7x right there had an x in it. That's why I set that factor equal to 0. What I typically do if I have a constant factor there is I just ignore it, because I know it's not going to give me any solutions to the equation, because there's no way -6 can be equal to 0. But I do set the other two factors equal to 0, and then I solve both of those equations. And so you get 2x equals 7, or x equals 7/2. And in the second one, you get 3x equals -8, or x equals -8/3. And those are my solutions here, 7/2 and -8/3. All right, so I'm hoping that so far this is all looking pretty straightforward and not too much of an issue with any of these problems. So now the next problem I want to look at, now this is actually out of section 7.6 in your book. So this is section 7.6, and this is page 874. And I'm looking at problem number 326. So 326 is y squared minus 8y plus 15 equals 0. All right, now this is definitely a quadratic equation. It definitely has a squared term. But notice this is not written as a multiplication problem. So it's not written as a times b equals 0. I don't have a multiplication problem here. And so this is where factoring comes into play, because we now know how to write this as a multiplication problem. And so factor this expression. So the equation is in the form a times b equals 0, right? That's what you're looking for. It's two numbers multiplied together to give 0. So this is a factoring problem, basically, right? Because we can use factoring to rewrite this as a multiplication problem. This is an easy trinomial, right? So it factors as y minus 5 times y minus 3, right? Negative 5 times negative 3 is positive 15, but they add to give negative 8. So we can write it as a multiplication problem really easily, and then we just simply set each factor equal to 0. Right? And you end up with y equals 5 and y equals 3. Please don't forget that you can always check these solutions. You can always check them. Now, I haven't been writing out the checks, but certainly it's something you could do. So like I could check y equals 5. So I go to the original equation. Always go to the original equation, by the way. Right? Y squared minus 8y plus 15 equals 0. And you actually substitute 5 in place of y. Every place you see a y, you put a 5. And I put a question mark there because I'm not sure this is equal. I'm checking it. So I get 25 minus 40 plus 15 equals 0. And sure enough, 25 minus 40 is negative 15. Plus 15 is 0. You get 0 equals 0. And it does check. Right? 3 will check also. Now, with quadratic equations, if you've done everything right, the solution should always check. There's no question about that. There are certain kinds of equations, by the way, and we will encounter them this semester, where even though you do everything right during the problem, you still come up with something at the end that's not a solution to the original equation. Believe it or not, that's going to be true. That's not something we have to worry about with quadratic equations, but there are times when we are going to have to worry about that. All right, next problem I want to look at. And please, again, stop me if you have a question, because I'm kind of working through these problems at a pretty steady pace. So this is number 327 on the same page. You have 5a squared minus 26a equals 24. And so the first thing I want you to notice in this problem is that this is not set equal to 0. And remember, if we're going to use the zero factor theorem, a times b equals 0 means a is 0 or b is 0. If we're going to use that theorem, we've got to have 0 on one side of the equation. So the first thing I do in this problem is I subtract 24 from both sides to get a 0 on the right side of the equation. By the way, it doesn't matter whether you get 0 on the right side of the equation or the left side. As long as 0 is on one side, that's all that matters. So I subtract 24, and now I've got the equation set equal to 0. All right, this is a not so easy trinomial. And so since it's a not so easy trinomial, I've got to go through and look at the factors and see how they work out. Remember, I need the inside 2 and the outside 2 to work out correctly here. Now, one thing that makes this problem a little bit easier is the fact that it's a 5a squared means that these terms have to be a 5a and an a. There's no other possibility there because 5 and 1 are the only factors of 5. So at least that's true. And then all we're looking at are factors of 24. And these are the factors of 24. 1 and 24, 2 and 12, 3 and 8, 4 and 6. So there's a lot of factors of 24. And I'm trying to see how I can get a negative 26 out of all this. All right? This is one of those places where if you're watching a recorded version of this at home, this is where I would stop the video, see if I can do this problem before I actually solve it. Because remember, I'm not going to be there on the test. You have to be able to do these kinds of things on your own. So the more practice you get with this, the better off you're going to be. In this case, if I put a 4 here and a 6 here, this actually doesn't work. I thought it was going to work here, but there's no way that this works because 4 and 6 is 24. And I do get a 20a here and a 6a here. It looks like maybe I can get a 26 out of that. But the problem is I have negative 24 in the trinomial. And so that means that the 6 and the 4 have to have opposite signs. And so that means the 20a and the 6a are going to have opposite signs also. And there's no way I can get a negative 26 out of that. So in fact, that doesn't work. I was thinking it did, but as we got into the problem, it doesn't work. All right, so this does not work. And I'm going to leave this on the notes for anybody who's looking at just the notes. All right, so I'm going to squeeze the factoring in right here. I've got 5a and a, and I'm trying to fit in factors of 24. So I know putting the 4 and the 6 like that doesn't work. But notice if I switch them, I will be able to get it to work. If I put the 4 here and the 6 here, now the outside 2 is 30, 30a, and the inside 2 is 4a, and now I can get a 26 out of that, right? I need a negative 26. I need the 6 to be negative, which means the 30 is negative, and then the 4 is going to be positive. So just switching them around got it to work. So you have to really be careful here and make sure you get the right combination. So I have 5a plus 4 equals 0 and a minus 6 equals 0. And I'm kind of running out of room here, so I'm going to squeeze in on this last equation, 5a plus 4 equals 0. Remember, you're subtracting 4 and dividing by 5. So that's negative 4/5. On the second one, I add 6 and I get 6. And so those are my solutions in this problem. And let's see, I think I can squeeze it in down here. So this is negative 4/5 and 6 are my solutions there. All right, so a little tiny bit more work to do on that problem. Let's see, the next one I want to look at. This is not in your textbook. Let's look at 81x squared equals 36. 81x squared, and yeah, that's fine. 81x squared equals 36. Now notice it's not set equal to 0. And so the first thing I'm going to do on this problem, if I'm going to solve this quadratic, is I need it set equal to 0. So I subtract 36. Now don't forget, so now we're going to try to factor this polynomial. And so the first thing I look for, don't forget to do this, is to look for a GCF. And in this case, there is something that's common. Right? In this case, the common factor is 9. Right? 9 is a common factor between 81 and 36. So I take out the 9 here, and I'm left with 9x squared minus 4. And then 9x squared minus 4 is the difference of two squares, because this is a 3x squared and a 2 squared. Right? And so this factors as 3x plus 2 times 3x minus 2. All right, so I did use the difference of squares there. And remember, a squared minus b squared factors a plus b times a minus b. And so that's what I did there, is I broke down 9x squared minus 4 is a square minus a square. And so that factors is 3x plus 2 times 3x minus 2. The 9 I just keep on writing down, but the 9 is a constant. And so that I do not get any solutions from that 9. I can ignore that in this step, right? So I just set the two variable factors equal to 0. And then I solve both of those, so I get 3x equals negative 2, or x is negative 2/3. And 3x equals positive 2, or x equals positive 2/3. And so this equation has two solutions, negative 2/3 and positive 2/3. Like that. All right, so I think we're doing really good here. The last problem I want to look at for factoring, so I have two more problems to look at. One is just a quadratic equation to solve, and then the second problem we're going to look at before we leave today is a word problem. Yay! It's always nice to finish the day with a word problem. All right, so this equation, x plus 6 times x minus 3 equals negative 8. Please, please, please don't do this. Please don't do this. And what I see frequently is I'll see a student say, oh, hey, x plus 6 is negative 8, or x minus 3 equals negative 8. Ugh, right? Remember, that's a misapplication of the zero factor theorem. Zero factor theorem only works for 0, right? That's why it's called the zero factor theorem. Zero factor theorem only works for 0. So I don't have a 0 on one side of the equation. So what do I have to do here? I have to kind of multiply everything out and get this equation in the right form where I can use the zero factor theorem. So I use the FOIL method and I multiply the left side out. Like that. And then I collect like terms. Like so. And then I add 8 to both sides. And now I have the equation in a form where maybe I can work with this, right? I've got this quadratic set equal to 0. And now I use the zero factor theorem, right? I factor the left side. So it factors x plus 5 times x minus 2. And then I set each factor equal to 0. Right? And there's no way you're going to get to that unless you multiplied everything out and moved all the terms over to the left side of the equation. So you end up with x equals negative 5 or x equals 2. Right? And remember, those are going to check. Right? If you checked, remember, if you check each equation, check the equation. Right? If you put in negative 5 there, you get negative 5 plus 6 times negative 5 minus 3 equals negative 8. So negative 5 plus 6 is 1. Negative 5 minus 3 is negative 8. And sure enough, that's negative 8. Right? So negative 5 checks. If you check 2, I usually try to write the original equation down when I'm checking it. Check 2, you get 2 plus 6 times 2 minus 3 equals negative 8. 2 plus 6 is 8. 2 minus 3 is negative 1. And sure enough, that's negative 8. Right? And so those both check. Remember, really good that you can, when you solve these equations, you can always check to see if you're right at the end by checking the solutions to the equation. So don't ever forget that you can do that. All right, so that's all looking good. The next problem I'm going to look at is problem number 346. And this will be our last problem of the day. Number 346 is a word problem on page 874, and basically goes like this. I think I'm going to leave some of it out, but it basically says that there's a rectangular wall, has a area of 15 square feet. 15 square feet. And then the height of the wall is 2 feet less than its length. And then basically it's find the length and the height. Now, when we find the length and the height, you might also see it say find the dimensions, right? Find dimensions means the same thing as finding length and height. Also, sometimes with a rectangle, so this is a wall, it's vertical, that's why they're using the word height there, but sometimes with a rectangle you'll see length and width written down instead. So, either way. Now, so area of a rectangle, area of a rectangle, remember, is length times width equals area. Or, in this case, it would be length times height equals area. In this case, height and width would mean the same thing for a rectangle. So this is the question, or the sentence rather, that we got to start with. It says the height is 2 less than the length. Right? And so what we do here is we're going to start out by letting the length be equal to x. Then notice the height is given in terms of the length, and it says the height of the wall is, so height equals, 2 less means we're subtracting 2 from the length. And so the height is going to be x minus 2. And so when you write those two things down, right, this would be L and this would be H right here. And what have we got here? We know that length times height is equal to area. And so that means that x times x minus 2 has got to be equal to 15 because that's the area. And so notice when we set this up, sure enough, we end up with a quadratic equation. Right, and so this is, we can solve this question by solving this quadratic equation. So you treat this just like we were doing the other problems. You'd want to get 15 on one, you'd want to get 0 on one side of the equation. So I'd multiply the left side out, get x squared minus 2x equals 15. And then I'd subtract 15. And then finally I would factor. And this is an easy trinomial. It factors x minus 5 times x plus 3. And so I set each of these factors equal to 0. And so you get x equals 5 and x equals negative 3. Now remember what x represents here is, Tricia, your question. Tricia, do you have a question? All right, I thought maybe Tricia had a question there. Whoops. So what happens now is that, remember that x represents the length, and the length can't be negative. And since the length can't be negative, we just throw negative 3 out. So negative 3 is actually a solution to the equation, but it can't be a solution to the problem that we're solving. So that means that the length here, which is x, has got to be equal to 5. And then the height is x minus 2. And so what's that going to be? That's going to be 5 minus 2, or 3. And so this is a 5 foot by 3 foot wall. Now, if you knew the original information, could you have guessed the solution, right? You know that the height is 2 feet less than the length. You know the area is 15. Could you have guessed 5 by 3 here? And the answer is absolutely, positively yes, you could have guessed that. Is guessing the solution to a problem like this a good way to solve the problem? Now, this will separate me from a lot of math teachers, because is guessing the solution to a problem like that a good way to solve the problem? Yeah, sure it is. If you are actually trying to deal with the dimensions of a wall for some construction purposes, and you were able to kind of use trial and error to guess at the solution, and you were able to come up with it, go for it. Absolutely. That's what you're trying to do, is solve the problem, and not a problem at all with doing that. But this is an algebra class, and so what are we doing? We are practicing using algebra to solve these problems. And so even though guessing a solution to something like this is not a bad way to solve a problem in a practical sense, that's not what we're practicing in algebra. We're practicing using algebra to solve these problems. And so I want to see the algebra in a problem like this. What I will say is, in directions on a problem like this on a test, is I'll say solve the following word problem or something like that using a quadratic equation or by setting up and solving a quadratic equation. So I'll actually ask you formally to use algebra to solve the problem. So, all right. So we've gotten a lot of good work done today, and so practice homework from the textbook on page 859, problems 279 through 309, and I would do the odds there. Remember that all the odd answers are in the back of your book, in the very back of the book. So if you've got the downloaded version of the book, you ought to be able to scroll to the very back of it, and you'll find the answers to all the odd problems. And so on page 359, those are really good factoring problems to practice, and so I would definitely do that. And then on page 874, so by the way, this is section 7.5, this is section 7.6. These are quadratic equations. And so 315 through 341. And on those, probably every other odd would be okay. And then on the word problem, I definitely want you to do this word problem. This is number 345. That's a word problem, and so that gives you at least a little bit more practice with word problems there. Okay, so for any of you who are with me today live, anybody have any questions to close out class today?
No questions right now.
Okay, Taylor, you're okay? Gianna?
No, sir.
Okay. Raina? And Tricia? Everybody's okay?
I'm okay.
All right, don't hesitate. I'll be online again in about 30 or 40 minutes for online office hours, so don't hesitate to come by. Otherwise, you guys all have a great weekend, and I will hope to see you next Tuesday.
Okay, thank you.
Thank you.
All right, take care.